Section 1. The immediate physical consequences, oceans, atmosphere, and the surface. Imagine standing on the earth as it comes to a sudden stop. The ground beneath your feet, usually steady and familiar, is no longer moving beneath you, yet everything that was in motion keeps going. Oceans surge violently, winds roar, and the air itself seems alive with sudden fury. The first and most dramatic impact would be on the oceans. The Earth's rotation causes the water at the equator to bulge outward slightly, giving the planet its characteristic oblate shape. If the spin stops, this centrifugal effect disappears, and the oceans are no longer held away from the poles. Water begins to flow slowly but inexorably toward the higher latitudes, a gradual migration that would reshape coastlines over hours and days. Equatorial cities, normally perched above sea level, would find themselves slowly submerged, while polar regions see a quiet rise of new oceans. It is a transformation both terrifying and strangely serene, a rebalancing of the planet's fluid systems, like water finally settling in a tilted basin. At the same time, the momentum of the oceans themselves would be catastrophic. Currents, waves, and tides that were once gently guided by rotation would continue moving eastward at hundreds of kilometers per hour. Coastal waters would surge inland, carrying everything in their path. Yet within this imagined chaos, one can also see the natural laws at work, forces obeying physics with quiet inevitability, redistributing mass across the globe in a precise, relentless way. The atmosphere, too, would react with astonishing energy. Earth's rotation drives the Coriolis effect, which influences wind patterns across the planet. Without spin, jet streams vanish, trade winds collapse, and the air itself retains the eastward momentum it had before the halt. Gale force winds would sweep across continents, flattening trees, shifting clouds, and reshaping landscapes. Even in this violent motion, there is a strange order. The planet is responding predictably, governed entirely by physical laws, like a vast mechanical clock winding down with unerring precision. The land itself is not immune. Mountains, plains, and valleys would experience forces that were never present before. Soils and sediment, loosely held together, might shift slightly, and tectonic plates could experience stress as the redistribution of water and atmospheric pressure changes the loads on the crust. The Earth's crust, usually moving slowly in imperceptible increments, might feel a subtle, almost imperceptible realignment, like a deep exhale of the planet itself. It is important to note that while the immediate effects are violent, the most profound changes are subtle and gradual. Water slowly flowing to higher latitudes, air redistributing itself over oceans and continents, and sediments adjusting under new pressures. These are changes that take hours, days, and years, yet they quietly transform the face of the planet into a version never before seen. For life, these changes would be both terrifying and awe-inspiring. Marine organisms would face sudden floods or exposed waters. Terrestrial animals would encounter unprecedented winds and pressure shifts, and humans would confront the reality that their familiar world is being rewritten in real time. Yet even in this imagined scenario, there is a strange calmness in the logic of the process. It is not random destruction. It is a precise orchestration of physical forces responding to a new planetary condition. Even the sunlit horizon would appear different. With the rotation gone, the movement of the sun across the sky would stop, creating either permanent day or permanent night, depending on your location. This immediate change in light exposure would further impact the atmosphere, altering wind patterns and temperature distributions. The calm of night and day would give way to a slow, continuous exposure that the planet must absorb and redistribute, much like a giant heat engine finding a new balance. Interestingly, despite the dramatic changes in oceans, air, and land, gravity itself remains constant. The pull that holds oceans to the surface, that anchors mountains, forests, and people, does not disappear. It is the invisible thread holding everything together, even as motion itself undergoes profound transformation. In the quiet aftermath, as waters settle and winds slow, the planet begins to take a new shape, a silent testimony to the power of forces at work. The immediate physical consequences of a sudden stop are therefore a blend of violence and calm, destruction and realignment. The oceans surge but settle, winds howl but redistribute evenly, sediment shifts yet finds new stability. The earth, in a sense, is reorienting itself, like a living organism adjusting to a new condition, moving from chaos toward a new, stable equilibrium. This is the essence of imagining the day the earth stops spinning, a planet in motion, suddenly forced to pause, responding with both fury and order, revealing the delicate balance of forces that make life and the familiar world possible. In the next section, we will explore the long-term effects on day and night cycles, climate, and temperature extremes as the planet adjusts to a motionless rotation. Section 2. The long-term climate effects, sunlit and dark hemispheres. When the Earth stops spinning, the consequences extend far beyond the immediate chaos of oceans and winds. One of the most profound transformations lies in the balance of light and temperature across the planet. Without rotation, one hemisphere faces the sun continuously, basking in endless daylight, while the opposite side remains in eternal night. This imbalance sets the stage for dramatic changes in climate, weather, and the very way energy moves through the atmosphere. On the sunlit side, the constant exposure to sunlight would gradually heat the surface and the atmosphere. Temperatures could rise far beyond what is normal today, creating a region of extreme warmth stretching across continents and oceans. Deserts, mountains, and forests alike would experience continuous solar energy, altering evaporation rates and surface temperatures. Water from oceans, lakes, and rivers would heat relentlessly, feeding a cycle of evaporation and condensation, creating clouds that may gather but move in unpredictable patterns without the rotation-driven Coriolis effect. This hemisphere would not just be hot, it would be perpetually static in its climate patterns. Daytime temperatures might reach extremes unimaginable in our current world, while winds, freed from rotational constraints, would blow from high-pressure zones to low-pressure zones in massive, slow-moving currents. Storms as we know them would disappear, replaced by a calmer yet extreme atmosphere, with heat gradients dictating airflow in a more direct, vertical manner. The sunlit hemisphere would essentially become a permanent day, a slow, deliberate furnace where energy accumulates over months and years. Meanwhile, on the dark hemisphere, a very different story unfolds. With no rotation to bring sunlight, this half of the planet would cool continuously, eventually freezing oceans, rivers, and lakes. Air temperatures could plummet to levels far colder than the coldest regions we know today. Without solar heating, the atmosphere itself would contract, creating dense, frigid air masses. Winds would still flow, moving from areas of higher pressure to lower pressure. But the driving force of rotational momentum would be gone. The dark hemisphere would transform into a world of slow, glacial calm, where temperatures hover near freezing, clouds are sparse, and the only motion is the gentle drift of the remaining air. The contrast between the two hemispheres would be dramatic, yet strangely beautiful. From a high vantage point, one could imagine the planet divided into two realms, a bright, heated land glowing under perpetual sunlight, and a shadowed, icy expanse of calm darkness. Oceans on the sunlit side would churn gently under constant warmth, while on the dark side, waters would solidify, forming frozen sheets that stretch across continents and seas. Over time, the differences in temperature between the two hemispheres would drive slow, massive circulations in the atmosphere. Without the Coriolis effect, winds would flow more directly, moving from the hot, sunlit regions toward the cold, dark side. These air currents would carry heat and moisture across the terminator, the twilight line between day and night, creating a narrow belt of perpetual dusk and dawn. This transitional zone, where extremes of temperature meet, could support forms of life that adapt to constant change, existing in a state of balance between scorching heat and freezing cold. The oceans would also play a crucial role in moderating climate. Even though the sunlit hemisphere would heat relentlessly, water has a high heat capacity and would absorb enormous amounts of energy, slowly transferring it toward the night side. This redistribution would occur not through rotation, but through convection currents and gravity-driven flows, creating new patterns of circulation that could stabilize regions along the edges of light and darkness. Yet this balance would be delicate. Minor shifts could produce extreme weather in the transitional zones, where warm and cold air meet in subtle, almost imperceptible turbulence. Interestingly, the absence of rotation would affect the planet's overall shape and gravitational effects, further influencing climate. Currently, the Earth's equatorial bulge helps distribute water and air more evenly. Without rotation, oceans would migrate toward the poles, altering sea levels and creating new coastlines that change how energy is absorbed and radiated. Mountains might cast longer shadows in permanent daylight or become frigid bastions in eternal night, affecting wind flow and local weather patterns. Life, too, would feel the long-term climate effects. Plants on the sunlit hemisphere would need to endure constant light, forcing adaptations in photosynthesis and growth cycles. Animals would face challenges of temperature regulation, and species would need to migrate toward the narrow habitable zone near the terminator. On the dark side, life would become nocturnal by default, adapted to cold and long shadows, with limited energy resources available from frozen oceans and sparse vegetation. The calm in this imagined scenario is profound despite the extremes. Without rotation, there is no storm-driven chaos as we know it. The planet enters a slow, deliberate rhythm, dictated entirely by the distribution of sunlight, heat, and gravity. It is a quiet reorganization of the Earth's energy system, revealing the subtle beauty in physics and planetary mechanics. Ultimately, the sunlit and dark hemispheres would exist in a delicate equilibrium, each shaping the other through slow, almost imperceptible flows of energy and matter. Time itself would feel different. Days and nights would lose meaning, replaced by a continuous experience of sunlight or darkness. Yet life, adaptation, and natural processes would persist in their own forms. Even in this radical transformation, there is a lesson in calm observation. The Earth's spin governs much of what we consider natural, but in its absence, the planet finds a new balance, a balance that is extreme yet orderly, dangerous yet predictable, chaotic in imagination yet serene in mechanics. The day the Earth stops spinning would mark the beginning of this long-term climate transformation, where heat and cold, light and dark, slowly carve new patterns across continents and oceans. And in this vision, we can sense the quiet majesty of a planet learning to exist in a new rhythm, a rhythm dictated not by motion, but by light, gravity, and time itself. Section 3. Gravity, centrifugal force, and the reshaping of oceans. The Earth spins with quiet majesty, completing one rotation every 24 hours. This motion, imperceptible to our daily lives, shapes much of the world we take for granted. It is responsible for the equatorial bulge, the flattening at the poles, and the subtle push that causes oceans to rise near the equator. But if the Earth were to stop spinning, these forces would vanish, and the planet would begin a profound physical transformation. At the equator, centrifugal force, the outward push caused by rotation, counteracts gravity slightly. This effect is small, almost unnoticed, yet it determines the distribution of water across the globe. With rotation gone, centrifugal force disappears, and gravity dominates completely. Water that was once held at the equator begins to flow toward the poles. This is not a sudden flood, but a slow, steady migration, a quiet reshaping of seas and coastlines as oceans seek a new equilibrium under a purely gravitational pull. The immediate consequences would be subtle yet immense. Equatorial regions, once slightly elevated by rotational bulge, would slowly subside relative to the poles. Cities near the equator could find themselves increasingly at risk of flooding, while polar regions, previously slightly depressed, would rise as water migrates toward them. Over centuries, the map of Earth would be rewritten, coastlines redrawn in ways no human has ever seen. The movement of water toward the poles would also alter ocean currents. Without the Coriolis effect, the result of Earth's spin, the familiar gyres and conveyor belts that circulate heat and nutrients across the oceans, would collapse. Currents would instead flow more directly, from equator to poles, slowly redistributing heat in a more linear fashion. This change, while gradual, would affect ecosystems, climate, and even the chemistry of the oceans. It is a calm, inevitable rebalancing, a subtle dance orchestrated by gravity and fluid dynamics. Gravity itself would feel unchanged, yet its relative dominance over the oceans and atmosphere would be magnified. Mountains, hills, and valleys, which today experience a slight reduction in effective weight due to centrifugal force, would feel their full gravitational pull. Rivers might flow slightly differently. Sediments might settle in new patterns, and landforms could adjust imperceptibly over long periods. The planet's surface would respond to this new gravitational balance with quiet patience, reshaping itself in slow, deliberate ways. The oceans, in particular, would undergo a majestic transformation. Equatorial waters would gradually drain, forming shallower seas, while polar oceans deepen, creating new marine environments and altering habitats for countless organisms. Ice at the poles could expand dramatically, since rising water levels and colder temperatures encourage glacial formation. Yet beneath the surface, currents and convection continue, moving heat and matter slowly but persistently, like a gentle heartbeat echoing through the frozen world. Interestingly, this process also highlights the delicate balance of forces that sustain life. The combination of rotation, gravity, and centrifugal force is responsible not just for the shape of the planet, but for the stability of climates, tides, and ecosystems. When one element, spin, disappears, the Earth is forced to find a new equilibrium, a quieter, slower rhythm, where oceans and air redistribute in accordance with fundamental physics. On land, the effects are subtler, but no less profound. Coastal plains may experience gentle inundation, mountain slopes may see adjusted river flows, and sedimentation patterns shift slowly with the new water distribution. Even human engineering, from levees to dams, would eventually be overcome as the planet seeks its gravitational balance. It is not destruction, it is realignment, a patient and inevitable recalibration of matter under a single dominant force. The disappearance of centrifugal force also affects atmospheric circulation. Air masses that once drifted in predictable patterns would now respond more directly to heat differentials between equator and poles. Storm systems would change or even vanish entirely, while winds could become slower but more persistent along specific gradients. The atmosphere would settle into a quieter pattern, moving gently but inexorably under the influence of gravity and thermal gradients. Over long timescales, the Earth would emerge as a new world. Oceans would find a polar-centered configuration. Mountains and rivers would adjust to new sediment distributions, and the atmosphere would adopt a calmer circulation pattern. The planet, though forever changed, would remain a place of order and structure, demonstrating the enduring power of natural forces to seek balance. Even the human perception of the world would change. What we call the equator, the poles, and coastlines would be altered. Time zones would become irrelevant in a world where rotation no longer defines day and night. Yet amidst these transformations, there's a profound calm. The planet does not resist these changes. It accommodates them. It is a slow, patient adjustment, a quiet reflection of the elegance of physics at work. In this vision, the Earth's oceans are like a liquid mirror of equilibrium, redistributing themselves without haste, forming new coastlines, reshaping continents, and quietly reminding us that even the most violent-seeming forces of rotation are ultimately governed by the steady pull of gravity. The day the Earth stops spinning would mark the beginning of this slow reshaping, where centrifugal force disappears, gravity reigns supreme, and oceans and air move toward a new, calm balance. It is a world in transformation, violent in imagination, but serene in the patient language of physics. A planet learning to exist in stillness, finding its equilibrium at last. Section 4. The impact on the atmosphere, winds, storms, and air pressure. The atmosphere, an invisible ocean of air enveloping the Earth, is in constant motion. It responds to heat from the sun, the rotation of the planet, and the distribution of land and water. But if the Earth were to suddenly stop spinning, this delicate ballet of wind and pressure would be profoundly altered. Rotation drives the Coriolis effect, a subtle force that deflects air currents to the right in the northern hemisphere and to the left in the southern hemisphere. This effect shapes trade winds, jet streams, cyclones, and anticyclones. Without rotation, the Coriolis force disappears, and air no longer swirls in the familiar patterns we have come to expect. The immediate effect would be striking. Air that was previously moving with the Earth's spin would continue its motion, creating a sudden, violent surge. Winds could sweep across continents at supersonic speeds, tearing through forests, fields, and cities. But after the initial upheaval, the atmosphere would settle into a new pattern, governed not by rotational forces, but by heat differences between the sunlit and dark sides of the planet. On the sunlit hemisphere, continuous solar heating would cause air to rise, creating persistent high-pressure zones at lower altitudes. Without rotation to redirect these currents, the wind would flow directly from high to low pressure, moving from hot equatorial regions toward cooler polar zones. Storms as we know them, hurricanes, tornadoes, cyclones, would vanish. The chaos of spinning systems is replaced by a slower, more predictable rhythm, where energy moves along straightforward pathways. Meanwhile, the dark hemisphere, shrouded in perpetual night, would develop dense, cold air masses. Gravity would pull this heavy air downward, increasing surface pressure and creating a calm, weighty atmosphere. Winds would still move from high-pressure regions to lower-pressure zones, but the motion would be more languid, less turbulent. It is a silent redistribution of energy, a planetary exhale after eons of rotational motion. Between these two extremes lies the terminator, the narrow band of perpetual twilight. Here, contrasting air masses meet, warm air from the sunlit side encountering cold air from the night side. This transition zone could support a narrow belt of mild climate, where winds are neither fierce nor stagnant. It is a place of balance, a calm corridor in a world of extremes, and perhaps the most habitable region on a motionless Earth. Air pressure, too, undergoes subtle yet profound changes. On a spinning Earth, centrifugal force slightly counteracts gravity at the equator, reducing effective weight and influencing atmospheric density. Without rotation, this counterbalance disappears. Air becomes denser at lower altitudes in equatorial regions, altering the buoyancy of clouds and the formation of precipitation. The result is a slower, more deliberate rhythm of weather, where storms take longer to form and dissipate, and the planet's climate moves with a gentle, almost meditative cadence. Interestingly, the absence of rotation affects the vertical movement of the atmosphere. Rising warm air from the sunlit side would flow directly toward the poles, and cooler air from the dark side would sink and flow back toward the equator. This direct convection creates massive, slow-moving air currents, replacing the complex, spinning systems we are familiar with. There is no chaos, only a patient redistribution of energy, a calm flow that mirrors the slow migration of oceans and land masses. Humidity and cloud formation would also shift. Evaporation on the sunlit side would remain strong, but clouds might drift more slowly, carried by the unhurried winds. Precipitation patterns would stabilize over time, forming persistent rain belts along transitional zones. The dark hemisphere, meanwhile, would see clouds thin and disperse, with snow and ice slowly accumulating in frigid regions. It is a planetary weather system stripped to its essentials, governed by temperature, pressure, and gravity alone. In imagining this atmosphere, there is a profound serenity. The planet has lost its rotational spin, but it does not collapse into chaos. Instead, the air settles into new flows, redistributing energy evenly, finding equilibrium through patient, invisible processes. Even the winds, once destructive and erratic, move in a steady rhythm, like a river of air slowly tracing the contours of a world at rest. Life, too, would adapt to these atmospheric changes. Birds, insects, and flying mammals would navigate different wind patterns, migrating along predictable currents rather than swirling storms. Plants would adjust to changes in precipitation and humidity, finding niches in the sunlit hemisphere, the dark hemisphere, or the twilight belt. In this calm, measured world, the atmosphere and life coexist in a new harmony, demonstrating the resilience of nature under entirely new conditions. Ultimately, the impact on the atmosphere reminds us of the elegance of planetary mechanics. Even when the Earth stops spinning, the forces that govern air movement, heat, pressure, and gravity continue to operate with quiet precision. The result is not destruction, but a rebalancing, a calm reshaping of wind, storms, and pressure into a more serene yet extreme system. The day the Earth stops spinning transforms the atmosphere into a living demonstration of physics. Winds flow with purpose, storms dissipate into quiet patterns, and the air itself becomes a patient witness to the new equilibrium of a motionless world.
Section 5. The effects on day and night, eternal day and endless night. One of the most profound consequences of a sudden stop in Earth's rotation would be the complete restructuring of day and night. For billions of years, the 24-hour cycle has defined life on this planet, shaping the behavior of animals, plants, and humans alike. The sun rises and sets, tides follow a rhythm, and temperatures fluctuate predictably. But if the Earth stopped spinning, this familiar cadence would vanish. Half of the planet would bask in perpetual sunlight, while the other half would dwell in endless darkness. The consequences, both immediate and gradual, would be dramatic. Yet in imagining them, there is a certain calm poetry, a world in frozen equilibrium, governed not by motion, but by position relative to the sun. On the sunlit side, the Earth would experience eternal day. There would be no sunrise, no sunset, no passage from morning to night. The sun would hang motionless in the sky, a constant and unyielding presence. Initially, this might feel like a miracle, a continuous embrace of warmth and light. But as hours turn to days, and days stretch into weeks, the effects of uninterrupted solar energy would become increasingly evident. Temperatures would rise steadily, soil would dry, rivers and lakes would evaporate, and vegetation would be stressed by continuous photosynthesis with no relief. Ecosystems designed for cyclical patterns would be forced to adapt or perish. The heat on the sunlit hemisphere would redistribute slowly. The oceans, absorbing massive amounts of solar energy, would transfer some of this warmth toward the cooler terminator, the narrow twilight zone separating day and night. Yet without rotation to circulate currents, this process would be far less efficient. Coastal regions near the equator might experience rising sea levels as ocean water expands from heating, while inland areas bake under unrelenting sunlight. Winds, moving directly from high to low pressure, would carry heat toward the poles, creating persistent air currents that may seem violent initially, but gradually settle into more predictable patterns. It is a new rhythm, calm and deliberate, dictated entirely by energy differences rather than rotational forces. Life on the sunlit side would face unique challenges. Plants, accustomed to cycles of light and darkness, would struggle with perpetual photosynthesis. Some might adapt by slowing their metabolism or shifting growth patterns, while others could fail entirely. Animals reliant on day-night cues for hunting, mating, or migration would need to adapt to the unchanging environment. Human societies, too, would be profoundly affected. Circadian rhythms, which regulate sleep, hormone production, and alertness, would be disrupted. Nighttime activities as we know them would vanish. Humans might need to create artificial cycles of light and dark to maintain physiological and psychological health. Meanwhile, the dark hemisphere would experience eternal night, a continuous absence of sunlight. Temperatures would plummet, gradually reaching extremes far beyond those seen today in polar regions. Oceans and lakes would freeze, forming thick sheets of ice. Snow and frost would accumulate endlessly, reshaping landscapes in slow, deliberate increments. Winds on the dark side would carry cold air toward warmer zones, creating a subtle, persistent flow rather than the turbulent storms familiar to us today. The atmosphere would move patiently, responding only to thermal and pressure gradients rather than the forces of spin. Despite the harsh conditions, the night side would have its own form of serene beauty. The absence of sunlight would create a world bathed in deep, eternal twilight, where stars dominate the sky, and the auroras, if Earth's magnetic field remains, could shine continuously. Ice-covered oceans would reflect starlight, creating a quiet luminescence. Even life, if adapted, might persist in this frozen world. Extremophile organisms could find niches in geothermal hotspots, volcanic regions, or under thick layers of ice, surviving in a patient, slow-moving ecosystem that thrives in the absence of light. Between these two extremes lies the terminator, the thin belt of perpetual twilight. Here, day and night converge, creating a narrow but potentially habitable zone. Temperatures are moderate compared to the extremes of eternal sun or night. Winds carry heat from the day side to the night side, while moisture and precipitation provide sustenance for life. Plants and animals could concentrate in this region, evolving to thrive in constant dusk or dawn. For humans, this twilight zone might become the primary habitable area, offering moderate light, manageable temperatures, and a stable climate. It is a narrow corridor of calm between two worlds of extremes, a place of balance where life might endure despite radical planetary changes. The psychological impact of eternal day or night would be profound. Humans derive orientation, mood, and sense of time from the rising and setting sun. On the sunlit side, the constant light might initially inspire wonder, but could lead to fatigue, restlessness, and stress over time. On the night side, the continuous darkness could evoke despair, disorientation, or depression. Yet, amidst these challenges, there is a certain meditative rhythm. Without the rush of daily cycles, life could slow, focus inward, and adapt to long-term patterns rather than short-term rhythms. The mind might learn to perceive time differently, embracing the endless present rather than the ticking of the clock. Even from a purely physical perspective, perpetual sunlight and darkness would affect planetary systems in ways subtle yet profound. The sunlit side would radiate more heat back into space, slowly warming the upper atmosphere, while the dark side radiates heat away, cooling the atmosphere and surface. This imbalance drives slow, continuous winds and currents, establishing a new global energy flow. Precipitation patterns would shift. Deserts might expand on the sunlit side, and ice sheets grow on the night side. Yet this system is not chaotic. It is governed by the immutable laws of physics, a quiet and elegant redistribution of energy that gradually finds equilibrium. The eternal day and night scenario also reminds us of the fragility and adaptability of life. Ecosystems built around rotation-based cycles would collapse or transform, yet life itself has remarkable resilience. Microbes, insects, and plants could find ways to endure extreme heat, cold, or perpetual twilight. Evolutionary pressures would create niches uniquely suited to this static rotation, where survival depends not on speed or movement, but on patience and adaptation. In this way, the Earth, though motionless, continues to be a dynamic, living system, shaped not by spin, but by the persistent flow of energy and the quiet resilience of life. In contemplating a world of eternal day and endless night, there is a strange serenity. The extremes are stark, the consequences profound, yet they unfold with a slow, deliberate pace. The planet is not screaming in chaos. It is whispering a new rhythm, one dictated by light, heat, and gravity alone. In this vision, we can sense the elegance of physics, the patient adaptation of life, and the quiet poetry of a planet at rest yet still alive. Ultimately, the cessation of rotation transforms the very experience of time and space on Earth. Day and night, as we know them, cease to exist, replaced by the eternal constancy of light or darkness. Life adapts, climates stabilize, and the planet finds a new balance. The Earth has paused its spin, yet the world continues in a calm, ordered, and profoundly reflective state, reminding us that motion is not the only source of life and rhythm. Even stillness carries its own deep and enduring flow. Section 6. The effect on the oceans, tides, currents, and marine life. The oceans, vast and patient, have always been intimately connected to the spin of the Earth. Currents sweep across the globe, distributing heat, nutrients, and energy, while tides rise and fall in response to the gravitational pull of the moon, moderated by the planet's rotation. But in a world where the Earth stops spinning, the oceans enter a new regime, a realm of slow, deliberate transformation, marked not by chaotic motion, but by the quiet redistribution of water and energy. The first and most immediate consequence is the loss of centrifugal force. At the equator, water is slightly pushed outward by the rotation, giving the oceans their subtle equatorial bulge. Without rotation, this outward force disappears. Equatorial waters begin to flow gently toward higher latitudes, moving toward the poles under the unyielding influence of gravity. It is a migration that takes hours, days, and even centuries, slowly reshaping coastlines, redistributing volumes of water, and altering the balance of the seas. This redistribution of water has profound implications for ocean currents. On a spinning Earth, currents like the Gulf Stream or the Kuroshio Current transport warm water from equatorial regions to higher latitudes, and cold water back toward the tropics. Without rotation, these gyres collapse. Currents would instead flow more directly along temperature gradients, moving from the sunlit, warm hemisphere toward the cold, dark hemisphere. The movement is slow, predictable, and patient, guided by the subtle gradients of heat and pressure rather than by the Coriolis effect. Marine life, accustomed to the rhythmic flow of currents, would need to adapt, relocating to areas where nutrients and temperatures remain viable. Tides, too, would undergo a transformation. The moon's gravitational pull continues to influence the oceans, but the familiar rise and fall every 12 hours depends on the rotation of the Earth beneath the tidal bulge. In a stationary world, tides would no longer move predictably across coastlines. Instead, high and low tides might remain in the same regions, creating permanent bulges along the sublunar and antipodal points. This static tidal pattern could flood some regions,
while leaving others unusually dry,
dramatically reshaping ecosystems along coastlines. Yet in this apparent stillness, there is an elegance, a new order imposed by gravitational forces, where water finds a calm but deliberate configuration. The distribution of heat in the oceans would also change. The sunlit hemisphere, heated continuously, transfers energy into the water, which then slowly moves toward the night side. This slow conveyor of thermal energy creates subtle convection currents that moderate temperature extremes, particularly near the terminator, the thin belt between perpetual day and eternal night. Marine life could find refuge in this transition zone, where warmth and light remain balanced. Even in a static world, the oceans continue to breathe, carrying energy, life, and potential across the planet. Ice formation would be extensive on the dark hemisphere. As oceans cool in the absence of sunlight, sheets of ice would form, thickening gradually over centuries. Polar regions would expand. Glaciers would extend further into previously temperate zones, and marine life beneath the ice would adapt to slow currents and reduced light. Yet beneath the frozen surface, life would persist in quiet niches. Deep-sea currents, geothermal vents, and areas of residual warmth would allow organisms to survive, a testament to the resilience of life even in extreme stasis. The loss of rotation would also influence ocean salinity and density. As water flows from equator to poles, differences in temperature and salinity would create subtle stratification. Denser, colder water sinks, forming deep currents that redistribute nutrients slowly over vast distances. Marine ecosystems would adjust to this new pattern, finding niches in zones where the water remains nutrient-rich and temperatures tolerable. It is a system of quiet equilibrium, governed by physics rather than the habitual rhythms we have grown accustomed to. Coastal regions would experience a profound transformation. Rivers that once flowed into predictable tidal zones may no longer meet the ocean in the same way. Shorelines would change gradually, with former beaches submerged and new land exposed as water migrates toward polar regions. Wetlands could dry, while new marshes form near rising polar seas. Even in this upheaval, there is a calm inevitability. The oceans follow the laws of gravity and fluid dynamics, reshaping the Earth in patient, deliberate motions rather than chaotic destruction. Life in the oceans, from plankton to whales, would face challenges, but also opportunities. Species reliant on predictable currents and tides might struggle, while others could thrive in the new equilibrium. The twilight zone along the terminator, where temperatures and light levels are moderate, could become a refuge for both marine and coastal life. Coral reefs might migrate toward cooler equatorial zones, while polar organisms adapt to expanding ice sheets. Life does not cease. It reorganizes, slowly finding balance in a new, motionless world. The oceans, in essence, become a reflection of the Earth's new rhythm. Gone is the familiar spin-driven chaos. Instead, there is a slow, patient redistribution of water, heat, and energy. Currents flow gently, ice expands quietly, and ecosystems adapt in silence. Even in the absence of rotation,
the oceans remain alive, a testimony to the enduring interplay of energy, matter, and life. Finally, the oceans would serve as a bridge between the sunlit and dark hemispheres. They carry heat from one side to the other, soften temperature extremes, and provide a medium for life to persist despite radical environmental changes. The Terminator becomes not only a habitable zone for land-based life, but also a vital corridor for marine organisms, linking the extremes of eternal day and endless night through slow, deliberate flows of water. The day the Earth stops spinning transforms the oceans into something both alien and familiar. They are no longer dynamic in the ways we expect, but they continue to move, breathe, and adapt. Currents flow with calm precision, tides settle into static patterns, and life navigates a slow, patient new order. It is a vision of a world reshaped not by violence, but by the quiet, inexorable laws of physics, where the oceans remain a source of energy, life, and balance in a stationary, yet profoundly alive Earth.
Section 7. The Fate of the Biosphere. Life under eternal day and night. Life on Earth has evolved under a rhythm defined by rotation. The predictable cycle of day and night, the gentle ebb and flow of tides, and the seasonal variations of sunlight have shaped ecosystems over billions of years. If the Earth were to suddenly stop spinning, the biosphere would face extreme, unprecedented conditions. Half of the planet would be bathed in eternal daylight. The other half plunged into endless night. Yet even in this dramatic scenario, life is remarkable in its resilience, adapting to extremes in ways that reflect both fragility and astonishing creativity. On the sunlit side, the constant exposure to solar radiation would challenge every living organism. Temperatures would rise continuously, soils would dry, and water resources could evaporate rapidly. Plants accustomed to day-night cycles would struggle with unending photosynthesis. Some might slow their metabolic processes, entering a near-dormant state during peak heat, while others could fail entirely. Over time, new forms of vegetation might evolve, optimized for perpetual sunlight. Thick leaves to retain water, reflective surfaces to minimize heat absorption, and root systems designed to extract moisture from increasingly arid soils. Animals on the sunlit side would confront equally profound challenges. Creatures that rely on nocturnal activity would need to adjust their behavior to a world without night. Predators and prey would experience constant exposure, changing hunting patterns and social structures. Some species might seek shelter during the hottest periods, using caves, burrows, or dense foliage to avoid overheating, while others could evolve physiological adaptations to tolerate prolonged heat. Ecosystems would transform gradually, balancing energy, water, and food availability in ways that differ dramatically from familiar patterns. Humans, too, would be profoundly affected. Circadian rhythms, which regulate sleep, alertness, and hormonal cycles, would be disrupted by the absence of day-night cues. People might create artificial schedules, using light and dark indoors to simulate night and day.
But the psychological impact would be deep. Continuous light could induce stress, fatigue, and mood disturbances. Societies might cluster near the terminator, the twilight belt, where temperatures are moderate and cycles of light are less extreme. In this narrow zone of balance, humans could maintain agriculture, settle cities, and sustain ecosystems in a way that mirrors the slow rhythm of the natural world. Meanwhile, on the dark side, life would exist under constant cold and darkness. Plants dependent on sunlight would perish, leaving ecosystems dominated by organisms adapted to darkness and low temperatures. Photosynthesis would be impossible for most species, so life would depend on alternative energy sources, geothermal heat, chemosynthesis in microbial communities, or nutrients carried from the terminator. Ice sheets would expand across oceans and land, creating new frozen habitats. Yet even here, life would persist. Microbes could thrive near volcanic vents. Fungi might exploit decomposing matter, and animals would adapt to hunting or scavenging in perpetual night. The extreme conditions would favor endurance and resilience over speed or abundance, creating a slower, quieter biosphere. The twilight zone, the thin strip of perpetual dawn or dusk, would become a sanctuary for life. Temperatures are moderated by the nearby sunlit hemisphere, while light levels are sufficient to sustain photosynthesis. This zone could become the epicenter of biodiversity, hosting plants, animals, and humans in a delicate balance of light and dark. Here, ecosystems could evolve new interdependencies, guided by the slow, deliberate rhythms imposed by the stationary Earth. Predators and prey would adapt to a consistent pattern of activity. Seasonal cycles would change or disappear, and life would settle into a calm, persistent equilibrium. The oceans would also play a critical role in supporting life. Currents, though slower and more direct than before, would transport nutrients and thermal energy from the sunlit side to the dark side, sustaining marine organisms along the way. Coral reefs might migrate closer to the twilight zone, where light and temperature are moderate, while deep-sea life continues largely unaffected by surface conditions. Fish, plankton, and larger marine mammals would adapt to slower currents and altered seasonal cues, finding niches in the new oceanic balance. Even in extreme conditions, life has an uncanny ability to adapt and persist. Microorganisms would likely thrive in both perpetual sunlight and darkness, colonizing niches too harsh for larger organisms. Mutations and natural selection would accelerate in the extreme environments, leading to new species tailored for constant light, constant dark, or the balanced twilight. Over generations, life would reorganize itself, not around the familiar cycles of day and night, but around new patterns of temperature, energy availability, and ecological opportunity. The biosphere's transformation would also illustrate a profound lesson about resilience. While the immediate consequences of a stationary Earth seem catastrophic, nature is patient. Ecosystems collapse in some regions, but flourish in others. Life does not vanish. It shifts, adapts, and endures. There is a quiet beauty in this process, a reminder that even in extreme circumstances, equilibrium can be found, albeit through different forms and pathways. Psychologically and emotionally, contemplating this scenario invites calm reflection. Humans may initially fear the extremes, but the eventual adaptation of life offers hope. We are reminded that Earth is not static. Even when rotation stops, the planet continues to function, to redistribute energy, and to host life in forms that are unexpected yet harmonious. The stationary Earth becomes a lesson in patience, resilience, and adaptation, demonstrating that even under extreme conditions, life continues its quiet, persistent rhythm. Ultimately, the fate of the biosphere under eternal day and endless night is one of transformation rather than annihilation. Sunlit regions adapt to constant heat. Dark regions survive in frozen isolation, and the twilight zone becomes a haven for complex life. The oceans, atmosphere, and landforms support new patterns of existence, while organisms evolve to meet the challenges of unchanging light and temperature. In this stationary world, life endures not through speed or chaos, but through adaptation, patience, and subtle equilibrium. The day the Earth stops spinning would be the beginning of a new chapter for life, a world where survival depends not on familiar cycles, but on resilience, resourcefulness, and the ability to thrive under extremes. It is a vision of the biosphere, both alien and deeply familiar, a world of calm endurance, where life, in all its diversity, persists despite the absence of the motion that once defined time itself.
Section 8. Geological consequences. Mountains, volcanoes, and the shifting crust.
The Earth's surface is in constant motion, shaped not only by the slow drift of tectonic plates, but also by the subtle forces generated by its rotation. The spin of the planet influences everything from the distribution of oceans to the slight flattening at the poles. If the Earth were to suddenly stop spinning, the impact on its geology would be profound, revealing a quiet yet inexorable transformation of mountains, volcanoes, and the shifting crust beneath our feet. One of the most immediate effects arises from the redistribution of water. Centrifugal force caused by the Earth's rotation pushes water toward the equator. Without it, oceans migrate toward the poles, redistributing mass across the planet. This shift exerts new stresses on the crust, particularly along coastlines and continental shelves. Regions previously burdened by deep oceans might rise slowly, while polar areas, now inundated with redistributed water, sink under the added weight. Over centuries, these subtle changes would adjust the balance of tectonic forces, potentially altering patterns of earthquakes and volcanic activity. Mountains, too, would experience a subtle but profound transformation. The equatorial bulge, maintained by rotation, contributes to the stress and shape of mountain ranges. Without centrifugal force, the Earth becomes slightly less oblate, and the crust adjusts in response. Equatorial mountains could experience a very gradual reduction in apparent height, as the redistribution of mass eases stress along the underlying rock. Conversely, mountains closer to the poles might feel slightly increased pressure from accumulating polar water, influencing erosion patterns, landslides, and the slow creeping of rock layers. These are processes measured over centuries and millennia, imperceptible in the short term, but monumental in geological time. Volcanoes, intimately linked to tectonic stress and mantle convection, could behave differently in a stationary world. As the distribution of mass shifts and pressure zones change, magma pathways may redirect. Some volcanoes might experience reduced activity if crustal tension is relieved, while others could awaken in regions where pressure increases due to water redistribution or shifts in the lithosphere. The molten heart of the Earth continues its patient work, shaping the surface in response to forces both ancient and new. Even without rotation, volcanism remains a reminder of the living planet beneath our feet. Dynamic, resilient, and capable of quiet, slow transformation. Earthquakes, too, would reflect these subtle changes. While most earthquakes are driven by the movement of tectonic plates, the altered distribution of mass and pressure could trigger new stress points. Regions near the equator, previously held in balance by rotational centrifugal force, might experience small adjustments in stress, producing tremors as the crust seeks equilibrium. Polar regions, bearing the weight of newly migrated oceans and ice sheets, could likewise experience seismic events. Yet these changes unfold over long timescales, measured in decades and centuries, a patient geological rhythm rather than the sudden chaos of surface destruction. Even the planet's interior would respond to a stationary rotation. The molten core, which contributes to the magnetic field, continues its slow circulation, but the redistribution of mass above it could alter the convection patterns subtly. These changes could influence the strength and orientation of the magnetic field, with long-term effects on radiation protection, auroras, and the behavior of charged particles in the atmosphere. The interior, though hidden from view, participates in the same patient adjustment to a world no longer spinning. Erosion patterns on the surface would also change in response to new climate dynamics. Rivers, driven by the sunlit hemisphere's continuous heat and the dark hemisphere's freezing cold, would carve landscapes differently. Without daily wind-driven storms in their familiar forms, rainfall and runoff would redistribute sediments more slowly, forming new deltas and valleys in previously unexpected locations. Mountains would erode, glaciers would creep forward on the dark side, and coastal cliffs would adjust to rising polar waters. The land itself adapts gradually, quietly reshaping the world in response to the new forces of gravity and redistributed energy. Interestingly, this stillness could reveal new geological phenomena. With the disappearance of rotational stress, the Earth's crust might experience more uniform compression along certain fault lines, allowing for previously dormant zones to stabilize or shift very slowly. Ancient mountain ranges might become more resilient, while younger ranges adjust to new pressures. Volcanic hotspots, such as Hawaii or Iceland, might see altered lava flows as the crustal tension subtly shifts, changing the paths of rivers of molten rock in ways that unfold over centuries. The relationship between water, ice, and rock becomes more pronounced in this scenario. Polar ice sheets expand steadily under perpetual night, adding weight to the lithosphere. This weight depresses the crust, causing slow subsidence that reshapes surrounding landscapes. Meanwhile, the sunlit side, losing ocean mass to migration, experiences subtle uplift in continental regions previously submerged or burdened by water pressure. The planet becomes a slow-moving interplay of forces where gravity, mass, and material respond in a quiet ballet that can take generations to fully manifest. Human observation of these changes would be gradual, almost imperceptible within a single lifetime. Yet the long-term impact on civilizations is profound. Coastal cities may find themselves submerged or newly elevated. River systems could alter their courses. Mountains and valleys slowly reshape the terrain. Infrastructure, agriculture, and settlement patterns would need to adapt to a world whose geology, while slow, is inexorably changing. The day the Earth stops spinning is not the end of geological activity. Rather, it is the beginning of a new chapter in the planet's slow, patient evolution. Mountains continue to rise and erode. Volcanoes pulse beneath the surface. Oceans redistribute mass, and tectonic plates creep with deliberate intent. The Earth adapts, reorganizes, and balances itself under a new set of conditions, reminding us of the resilience and elegance inherent in a living planet. Even in a stationary world, the geology of Earth tells a story of quiet endurance. The planet's crust, oceans, and molten interior continue their patient rhythms, shaping the surface with both power and subtlety, demonstrating that stillness does not mean stagnation. It is a testament to the enduring forces of nature, a world that continues to evolve in calm, deliberate, and awe-inspiring ways. Section 9. The Human Experience, Society, Psychology, and Daily Life on a Stationary Earth. Life on Earth is deeply tied to rotation. From the rising and setting of the sun to the predictable rhythm of days and nights, human behavior, culture, and even biology have evolved in synchrony with the planet's spin. If the Earth were to suddenly stop rotating, the consequences for human societies would be profound, touching everything from daily routines to long-term survival strategies. Yet, in examining this new world, one can also perceive a strange calm, a reality reshaped by patience, adaptation, and the resilient ingenuity of humanity. One of the first challenges humans would face is timekeeping. Without rotation, the familiar 24-hour day ceases to exist. Half the planet would experience eternal sunlight, while the other half would dwell in endless darkness. Traditional concepts of day and night, morning and evening, would be meaningless. Humans would need to create artificial schedules to regulate sleep, work, and social interaction, relying on light, sound, and communal cues, rather than the natural progression of the sun. This new form of temporal structure might initially feel disorienting, yet it also opens possibilities for redefining productivity, leisure, and circadian balance. On the sunlit side, people would face continuous exposure to light and heat. Outdoor activity during perpetual day could be hazardous, as ultraviolet radiation and rising temperatures affect skin, health, and comfort. Shifts in architecture would occur. Buildings might include advanced shading systems, reflective materials, and subterranean dwellings to regulate temperature. Water management would become critical as evaporation accelerates and rivers redistribute toward the poles. Society would need to adapt its agriculture, energy production, and urban planning to thrive under a constant sun. Conversely, the dark side presents challenges of cold and isolation. In perpetual night, temperatures would plummet, forcing humans to rely heavily on insulated shelters, geothermal heat, or artificial light sources. Food production would be nearly impossible using conventional methods. Reliance on stored resources, hydroponics, or relocation near geothermal hotspots would become essential. Psychologically, humans living in eternal darkness could experience disorientation, depression, and fatigue. Yet here too, adaptation is possible. Humans have evolved behavioral flexibility, and social structures could provide support, community, and mental stimulation to maintain resilience. The twilight zone, the narrow strip of perpetual dawn or dusk between day and night, would likely become the primary habitat for large-scale human civilization. Temperatures are moderate, light levels sufficient for agriculture, and water and energy flow more predictably. Humans would cluster in these regions, forming cities and communities along a continuous corridor of balanced conditions. Life in the twilight zone would be slower, more deliberate, and deeply attuned to natural patterns rather than the abrupt cycles of sunrise and sunset. Here, humans might cultivate crops that thrive under constant but mild sunlight, harvest resources efficiently, and observe wildlife adapting to new planetary rhythms. The psychological implications of a stationary Earth are profound. Humans are accustomed to temporal markers that guide sleep, work, and social interaction. The absence of these markers requires new forms of temporal orientation and self-discipline. Yet there is also opportunity for introspection and mindfulness. With fewer sudden shifts and predictable cycles, daily life could adopt a meditative rhythm. Societies may become less reactive and more intentional, learning to live with long-term patterns rather than immediate fluctuations. Energy and technology would play a critical role. On the sunlit side, solar power becomes abundant, but also challenging due to overheating and continuous exposure. Energy storage and cooling systems would be essential. On the dark side, humans would rely heavily on geothermal energy, nuclear power, or imported energy to sustain life. Artificial lighting would simulate day-night cycles to support biological rhythms and psychological health. Communication and transportation networks would need to adjust to the new global geography of habitable zones, connecting communities across the extreme hemispheres. Education, culture, and social structures would also transform. Children growing up on a stationary Earth would learn to navigate environments radically different from our current world. Stories, art, and philosophy would likely reflect themes of permanence, balance, and adaptation, rather than cycles and transitions. Human creativity might flourish in unexpected ways, inspired by the extreme yet serene conditions of a motionless planet. Interestingly, the stationary Earth would also affect political and social organization. Nations and regions might cluster in habitable twilight zones, forming concentrated populations along a continuous strip of livable land. Cooperation in managing resources, such as water, food, and energy, would be paramount. Isolation between sunlit and the dark hemispheres could create distinct cultures and adaptations, each optimized for their environment, yet connected through trade and communication along the twilight corridor. In contemplating human experience on a stationary Earth, one sees both challenge and resilience. While environmental extremes test survival, human ingenuity adapts. Life slows, but it does not stop. Societies reorganize, behaviors recalibrate, and communities find new rhythms that reflect the patient flow of energy, light, and heat. In a way, the world becomes a living laboratory, a place where humans must rediscover equilibrium, patience, and adaptability on a planetary scale. Finally, there is a quiet philosophical lesson embedded in this scenario. The day the Earth stops spinning is not merely a catastrophe. It is a profound opportunity to observe life's resilience. Humans, like the oceans, the atmosphere, and the crust, must adjust slowly and patiently. The planet, though motionless, continues to function, to redistribute energy, and to sustain life. Even amidst extremes of perpetual sun and eternal night, humanity can find balance, calm, and a renewed sense of connection to the rhythms of the earth, however altered they may be. In the end, the human experience on a stationary Earth becomes a story of adaptation, endurance, and quiet triumph. Daily life is redefined, societies reorganize, and cultures evolve, in harmony with a world no longer defined by rotation. It is a vision of life at once alien and familiar, a patient, reflective rhythm emerging from the stillness of a motionless planet.
Section 10. The magnetic field and cosmic consequences, solar radiation and the vanishing spin. Earth's rotation is intimately tied to one of the planet's most vital invisible shields, the magnetic field. Generated by the motion of molten iron and nickel in the outer core, the magnetic field creates a protective bubble around the planet, deflecting charged particles from the sun and cosmic radiation from the depths of space. If the Earth were to suddenly stop spinning, the consequences for this magnetic shield and the environment it safeguards would be profound, subtle, and slow-moving, yet deeply consequential. The geodynamo that powers the magnetic field relies on the rotation of the Earth. As molten metal in the outer core moves, it generates electric currents, which in turn produce magnetic fields. Without the planet's spin, the geodynamo would weaken. The field might become asymmetric, fluctuate irregularly, or even collapse over time. Without this protective barrier, Earth's surface would be increasingly exposed to solar winds, streams of charged particles emitted by the sun, and cosmic rays from deep space. Solar radiation, normally deflected by the magnetosphere, would begin to interact more directly with the atmosphere. The consequences would vary depending on location. On the sunlit hemisphere, continuous solar exposure could intensify radiation levels, affecting both human and ecological systems. Technological infrastructure, especially satellites and communication networks, would experience heightened exposure to energetic particles. Radiation could gradually erode electronics, damage power grids, and interfere with navigation systems. The dark hemisphere, while shielded from sunlight, would also experience increased exposure to cosmic rays. Although cosmic rays are less intense than solar wind, their interaction with the atmosphere could produce secondary particles
subtly increasing background radiation. For life adapted to perpetual darkness, this represents a slow but persistent challenge. Organisms would need to evolve additional resistance to radiation damage, particularly microorganisms and long-lived species exposed continuously over generations. Auroras. The shimmering lights, usually confined to polar regions, would behave differently. Normally guided by the magnetic field, these luminous displays occur when charged particles are funneled toward the poles. A weakening or collapsing field would alter the auroral belts, potentially shifting them to unexpected latitudes or dispersing them entirely. Though a loss of organized auroras may seem small compared to other planetary changes, it is emblematic of the subtle cosmic consequences of a stationary Earth. Changes that are beautiful, mysterious, and far-reaching. The atmosphere itself interacts with cosmic and solar radiation in complex ways. High-energy particles, colliding with the upper atmosphere, produce ions, creating faint layers of electrical activity known as the ionosphere. Without a strong magnetic field, these particles penetrate deeper, altering ionization patterns and potentially affecting radio communication and atmospheric chemistry. Over centuries, changes in atmospheric composition might occur, especially in ozone levels, further influencing life and climate on the sunlit and twilight hemispheres. Earth's stationary spin also affects the flow of charged particles in space around the planet. Currently, the magnetic field channels these particles along curved paths, creating radiation belts that trap high-energy electrons and protons. Without rotation, these belts could disperse, exposing the surface and orbiting satellites to higher particle flux. For humans, this would mean that technology in orbit becomes more vulnerable, while long-term exposure on a surface, especially in the unshielded sunlit hemisphere, gradually increases risk of radiation-related damage. Interestingly, a weakened magnetic field would also affect atmospheric escape. Earth slowly loses hydrogen and helium to space, a process partially mitigated by the magnetosphere. Without strong magnetic protection, lighter particles in the upper atmosphere could escape more easily over millennia, altering atmospheric composition subtly but inexorably. Though these changes unfold slowly, they remind us that the Earth's spin, magnetic field, and atmosphere are part of a delicate, interdependent system, each sustaining the other in quiet equilibrium. For human civilization, the cosmic consequences of a stationary Earth would be multifaceted. Satellites would need enhanced shielding to survive increased particle radiation. Astronauts and high-altitude pilots would be exposed to elevated radiation, requiring new protocols for safety. Even simple technologies, such as power grids or telecommunications, would need to account for the increased interaction between energetic particles and conductive materials. These are challenges that unfold over decades and centuries, yet they illustrate the interconnectedness of rotation, magnetism, and life on the surface. Yet amid these cosmic consequences, there is a certain calm in perspective. The processes unfold slowly, allowing adaptation rather than sudden catastrophe. Life on Earth, humans included, could adjust through migration, engineering, and evolutionary adaptation. The weakening of the magnetic field does not immediately erase life or function. Rather, it gradually changes the environment, demanding patience, foresight, and resilience. The twilight zone, once again, plays a key role. Here, solar exposure is limited and temperatures moderate, offering some natural protection against the intensifying radiation on the sunlit side. Communities and ecosystems in this corridor would benefit from a balance between energy, light, and relative safety, much as they do for temperature and habitability. The twilight zone becomes a sanctuary, a natural mediator between extremes of light, darkness, and cosmic exposure. Ultimately, the vanishing spin and its impact on Earth's magnetic field remind us that even invisible forces are vital to life and stability. The planet's motion is not merely a matter of day and night, but a core element of its protective systems, its climate, and the delicate balance that sustains life. Even in a stationary world, the Earth continues to function, but the absence of rotation quietly reshapes the planet's relationship with the cosmos, inviting humans and other life forms to adapt, innovate, and endure. In this vision of a stationary Earth, there is a profound sense of both vulnerability and serenity. Though the magnetic shield weakens and cosmic exposure grows, the planet's rhythms continue. Life persists, technology adapts, and the balance of energy finds new forms. The cosmos interacts with Earth in a quiet, deliberate dance, reminding us that even in a world without spin, the universe continues its patient, enduring flow. Section 11. Long-term climate shifts from perpetual day to polar ice expansion. The Earth's rotation is one of the most fundamental factors shaping its climate. It influences wind patterns, ocean currents, the Coriolis effect, and the distribution of heat across the planet. If the Earth were to suddenly stop spinning, these dynamic systems would be profoundly altered. The result would be a world defined by extremes, the sunlit hemisphere enduring continuous heat, the dark hemisphere freezing in perpetual night, and the polar regions becoming zones of dramatic ice expansion. Yet, in the calm reflection of these changes, there is a quiet order, a deliberate restructuring of climate that unfolds slowly over decades, centuries, and millennia. The sunlit hemisphere would experience continuous heating with the sun fixed motionless in the sky. Temperatures would rise steadily, especially near the equator, creating vast deserts and parched landscapes. Without rotation to drive the daily cycle of heating and cooling, winds would shift from turbulent, chaotic flows to slower, more predictable patterns. Hot air from the equator would drift toward the terminator and the poles, transferring energy in a deliberate, almost meditative circulation. Cloud formation would be concentrated in specific regions, where moisture converges along the slower-moving currents, creating persistent storm zones rather than shifting weather patterns. Meanwhile, the dark hemisphere would plunge into endless cold. Lack of sunlight would cause surface temperatures to drop dramatically, freezing oceans and rivers. Ice sheets would expand steadily, thickening over centuries and slowly advancing toward the twilight zone. Precipitation would fall primarily as snow, accumulating continuously and gradually reshaping landscapes. Even in this extreme cold, the atmosphere would maintain gentle motion as heat from the sunlit hemisphere diffuses slowly toward the night side. It is a system of balance achieved over long durations,
where even in darkness, energy finds a patient path. The polar regions would become repositories of mass and energy redistribution. As ocean water migrates toward the poles, sea levels would rise locally, flooding low-lying land. At the same time, continuous freezing on the night side contributes to ice accumulation, depressing the crust and gradually altering pressure along tectonic boundaries. This slow interplay of water, ice, and land creates a dynamic yet quiet reorganization of the planet's climate system, demonstrating that even in a stationary world, motion exists in subtle and deliberate forms. Ocean currents, the lifeblood of global climate, would transform dramatically. Without rotation, gyres like the Gulf Stream and the Kuroshio Current would collapse. Instead, slow flows from the hot sunlit hemisphere to the cold, dark hemisphere would develop, carrying heat and nutrients gradually. These currents would moderate the extremes of temperature, especially near the terminator, and could create new habitable zones in previously inhospitable regions. Marine life would adapt to these slower flows, finding niches in predictable, gentle movements of water rather than chaotic, high-energy currents. Atmospheric circulation would also slow and reorganize. Without the Coriolis effect, winds would flow more directly from high-pressure zones to low-pressure zones. Storms, while less frequent, could be more persistent in specific regions, particularly along the boundary between extreme heat and extreme cold. Monsoons, hurricanes, and cyclones as we know them would largely disappear, replaced by calm, steady wind patterns. Rainfall would concentrate in predictable belts, shaping ecosystems in ways both alien and harmonious. Over decades and centuries, the sunlit hemisphere would see the gradual desiccation of landscapes. Soils would dry, rivers would shrink, and vegetation would adapt to continuous heat. The dark hemisphere, in contrast, would experience progressive glaciation, with ice sheets slowly extending into previously temperate zones. Coastal erosion would proceed differently as tides become static and ocean currents weaken. The twilight zone, where heat and cold meet, would likely become a refuge for both humans and wildlife, sustaining life in a narrow corridor of moderated climate. The slow redistribution of energy also affects long-term weather patterns. Temperature gradients between the sunlit and dark hemispheres would drive gentle airflows, moving heat from hot to cold regions. These flows would be subtle, almost imperceptible to daily observation, yet over time they establish a steady equilibrium. Clouds would form in predictable zones, bringing occasional precipitation to the twilight belt, sustaining ecosystems in a stable, calm rhythm. Interestingly, volcanic and geological activity would also influence climate. As water migrates and ice sheets expand, pressure on the crust changes, potentially triggering volcanic eruptions or tectonic adjustments. Volcanoes on the sunlit side could provide temporary cooling through aerosol release, while those in polar regions could sustain pockets of heat beneath expanding ice sheets. Even in a stationary world, geology interacts with climate in a patient, deliberate dance. Over centuries, the stationary Earth establishes a new climatic equilibrium. Extreme heat and cold persist at the poles and equator, while the terminator becomes a stable zone of moderate temperature. Life migrates toward the twilight, adapting to the slow and predictable rhythm of this altered climate.
Although the familiar patterns of day and night, seasons, and storms vanish, a subtle harmony emerges from the patient redistribution of energy, water, and mass. From a human perspective, these long-term climate shifts would require profound adaptation. Agriculture would need to concentrate in the twilight zone, using controlled irrigation and heat management. Settlements in the sunlit hemisphere would require protection from continuous heat, while those in the dark hemisphere would rely on insulation and energy sources to survive freezing conditions. Societies would need to plan over decades rather than days, anticipating gradual climate change rather than rapid seasonal shifts. Yet even in this world of extremes, there is a sense of calm and order. The Earth, though no longer spinning, continues to balance itself. Energy flows, water redistributes, ice accumulates and melts in measured patterns, and life persists where conditions allow. The planet's climate becomes less chaotic, more deliberate, and governed by patient natural laws rather than the frenetic rhythms of rotation. In imagining these long-term shifts, one sees a planet profoundly changed, yet quietly elegant. Sunlight and darkness carve the contours of habitable zones. Ice and ocean redistribute energy and mass, and wind and currents establish steady flows. Life, human and ecological, adapts, migrates, and survives. The day the Earth stops spinning does not end climate, but it transforms it into a calm, deliberate system, where extremes coexist with stability, and time is measured not by hours, but by centuries of slow, graceful change.
Section 12. Astronomical Effects. Stars, Planets, and Night Sky Observation. The spinning of Earth is the silent rhythm that orchestrates our perception of the cosmos. It brings the sun and moon across the sky, paints the familiar patterns of stars each night, and shapes our sense of celestial time. If the Earth were to stop spinning, the night sky would transform in ways both profound and subtle, revealing a cosmos that appears static yet alive, inviting reflection on our place in the universe. On the dark hemisphere, the stars would no longer sweep across the sky with the slow arc of nightly rotation. Instead, constellations would remain fixed in place, a celestial mural suspended above the frozen world. The familiar patterns of Orion, the Big Dipper, and the Milky Way would hang motionless, unchanging for centuries. This stillness would offer astronomers an unparalleled opportunity: the ability to observe stars, planets, and deep sky objects without the need for tracking instruments to compensate for Earth's rotation. Yet the static sky would also feel alien, a subtle disorientation for human perception, accustomed to movement, rhythm, and the gentle passing of time marked by celestial drift. Planets within the solar system would appear differently as well. Currently, their motion across the sky is combined with the Earth's rotation, creating complex patterns visible to the naked eye. Without rotation, their apparent movement slows to reflect only their orbital paths around the Sun. Venus, Mars, Jupiter, and Saturn would drift slowly against the fixed backdrop of stars, tracing gentle arcs across the sky over days, weeks, or months. Observers could witness the slow ballet of planets in exquisite detail, appreciating the mechanics of the solar system in a serene, deliberate manner.
The sun, fixed in the sky over the sunlit hemisphere, creates its own new perspective. No longer rising or setting, it becomes a permanent fixture, illuminating the landscape without variation. Sunlight would remain constant, intensifying shadows and highlighting topography in a way unfamiliar to the human eye. At noon, objects cast unchanging shadows, and familiar cycles of day and night vanish, leaving a still, quiet landscape bathed in continuous light. The moon, however, continues its orbit around the Earth. For observers in both hemispheres, its phases would progress, but its motion across the sky would no longer be aided by Earth's spin. The moon would rise and set solely due to its orbit, a slow, deliberate path against the backdrop of fixed stars. Eclipses, whether solar or lunar, would become events that unfold with heightened clarity, visible in their entirety over longer durations than previously possible. These celestial rhythms, though altered, would offer a new kind of serenity to those who watch the sky with patience. The Milky Way, usually appearing as a slowly shifting band across the night sky, would hang motionless in the dark hemisphere. Astronomers could track individual stars over extended periods without interference from Earth's rotation, opening opportunities for detailed observation of stellar motion, proper motion, and the behavior of nearby galaxies. The universe, in essence, becomes a calm, static laboratory for understanding cosmic mechanics, allowing for reflection on the immensity and quiet order of the cosmos. Even human perception of time would shift. Without rotation to define hours and minutes, celestial movements become markers of longer-term intervals, days, weeks, months, and years, as measured by the orbits of planets, moons, and distant stars. Time itself feels slower, more patient, reflecting the deliberate pace of celestial mechanics. This could inspire a renewed philosophical perspective, emphasizing longevity, observation, and the enduring rhythms of the universe, rather than the frenetic pace of daily life. Interestingly, the stationary Earth also offers new insights into astronomical alignments. Without the blurring of rotation, stars near the horizon would appear more stable, and long-exposure astrophotography would capture detail without streaking caused by rotation. Comets, meteor showers, and transient phenomena would be observed with unusual clarity, revealing the slow elegance of cosmic events. Observers could anticipate meteor paths with precision, witnessing natural processes that typically seem fleeting from a spinning vantage point. The twilight zone, where sunlight and darkness meet, offers a unique vantage for observing both extremes. Here, observers could witness the constant sun on one horizon and the slowly moving stars on the other, creating a surreal and meditative celestial experience. The fixed sun illuminates terrestrial landscapes, while the calm night sky gradually reveals the movement of distant celestial bodies, allowing humanity to connect with the cosmos in both light and shadow simultaneously. A stationary Earth would also transform our relationship to navigation and space exploration. Traditional celestial navigation relies on predictable motion of stars relative to Earth's rotation. With rotation halted, new methods of orientation and long-term tracking would be necessary. But the stability of the sky could also simplify certain astronomical calculations, permitting longer-term observation of orbital patterns and interstellar objects without the complication of Earth-induced movement. Ultimately, the non-spinning Earth reframes our perception of the cosmos. Stars become eternal sentinels, planets trace slow arcs, and the sun becomes a fixed beacon of light. Observers learn patience, observing the universe not as a fast-moving spectacle, but as a deliberate, enduring system of interwoven rhythms and forces. There is a profound calm in this perspective, a meditative opportunity to appreciate the order and continuity of the cosmos. In imagining a stationary Earth, the night sky emerges as a space of serenity and contemplation, while the planet itself has been thrown into extremes of temperature, climate, and rotation-induced chaos. The heavens offer constancy. Stars, planets, and galaxies remind us of the slow, patient rhythms of the universe, a cosmic backdrop against which the drama of Earth unfolds, yet one that continues in quiet, elegant motion, inspiring awe, reflection, and deep tranquility.
Section 13. The Twilight Zone. The most habitable band of the stationary Earth. Amid the extremes of a non-spinning Earth lies a delicate, narrow region known as the Twilight Zone, the boundary between eternal day and perpetual night. Here, temperatures are moderated, light levels are gentle, and conditions remain surprisingly stable. While the sunlit hemisphere scorches and the dark hemisphere freezes, the Twilight Zone emerges as a sanctuary for both life and humanity, a place where adaptation, patience, and balance define survival. In this narrow corridor, the sun hovers near the horizon, neither rising nor setting, creating perpetual dawn or dusk. The light is softer, shadows are long and unchanging, and the atmosphere carries the gentle, calm energy. Here, photosynthesis is possible, but not excessive. Water does not evaporate as rapidly as in the sunlit regions, nor freeze solid as on the dark side. The combination of warmth, light, and moisture fosters biodiversity. Plants evolve to thrive in continuous low-angle sunlight, developing broad leaves for capturing light without overheating, deep roots to stabilize against soil shifts, and adaptive growth patterns to maximize energy. Animals in the Twilight Zone exhibit remarkable adaptations. Predators and prey learn to coordinate activity in a steady environment rather than responding to day-night cycles. Nocturnal species from the dark side and diurnal species from the sunlit side could coexist, exploiting niches that balance light and temperature. Migratory patterns would stabilize, with creatures moving slowly along the corridor in response to resource availability rather than sudden climatic changes. The ecosystem develops a measured rhythm, a gentle pulse reflecting the calm, deliberate nature of the stationary planet. Humans would naturally gravitate to the Twilight Zone. Here, settlements could flourish with minimal energy intervention. Agriculture benefits from moderate sunlight. Water is neither scarce nor frozen,
and temperatures are tolerable year-round. Cities might spread in elongated bands along this corridor, optimizing access to habitable zones while minimizing exposure to extreme heat or cold. Cultural and societal rhythms would evolve slowly, shaped not by days and nights, but by careful observation of resource cycles, seasons, and long-term environmental changes. The twilight zone also offers strategic advantage for survival and innovation. Technology and energy systems could harness natural gradients. Solar panels optimized for constant low-angle light, geothermal energy in cooler areas, and wind systems responding to steady airflows between hot and cold hemispheres. Agricultural innovation would thrive in these regions, combining human ingenuity with natural equilibrium to sustain populations. The twilight zone becomes a living laboratory of resilience, patience, and subtle adaptation. Even the human psyche benefits from this environment. Continuous light without glare or oppressive darkness fosters calm, meditative awareness. The twilight zone's balance offers space for introspection, creativity, and reflection on the world's altered rhythms. Without the chaos of extremes, humans can develop deeper connection to both the environment and each other, learning to synchronize with the planet's patient, deliberate flow rather than impose artificial schedules. The twilight zone also serves as a bridge between extremes. It connects the sunlit and dark hemispheres ecologically, allowing species, nutrients, and water to migrate slowly. Ocean currents, winds, and migrating animals stabilize in this corridor, forming a hub of biodiversity and energy exchange. The twilight zone becomes the heart of life on a stationary Earth, a corridor where ecosystems and humans coexist harmoniously in a balance shaped by observation, adaptation, and patience. In the grand tapestry of a stationary Earth, the twilight zone is a quiet revelation. It illustrates that even amid extremes, there are regions of calm and continuity, where the planet's energy finds equilibrium and life discovers a way to endure. This narrow band exemplifies resilience, adaptation, and subtle beauty, a space where life continues in harmony with its environment, even as the world around it becomes alien and extreme. Reflections on a stationary Earth. The day the Earth stops spinning is a vision of extremes, of eternal day and endless night, of frozen seas and scorching lands. Yet in this transformed world, there is calm, order, and resilience. The oceans, atmosphere, and crust adjust slowly, creating new patterns of life, climate, and geological activity. Humans adapt, societies reorganize, and ecosystems evolve in harmony with altered conditions. Amid it all, the twilight zone emerges as a sanctuary, a narrow ribbon of balance where life flourishes, a reminder of nature's patient ingenuity. Observing this world invites reflection. The cosmos continues its eternal rhythm. The planet reshapes itself, and life endures through adaptation and patience. Even when motion ceases, the Earth remains alive, evolving in subtle, deliberate ways. The stationary Earth becomes a meditation on balance, resilience, and the quiet power of the natural world, a serene reminder that life, in all its forms, finds a way, even under the most extreme circumstances.